part where okay you have starting from the okay, wait. Okay, starting from the first part in chapter 2, I mentioned to you that this chapter will be divided into three parts where you'll be learning about U, which is electric potential energy, and then you'll be learning about electric potential, where you call it as voltage later on. But for this U and V, you need to be very careful because you need to use the equation whether for parallel plate or for point charges. So we have defined the U and V for parallel plates. So today I am going to introduce to you what is the formula for electric potential energy for point charges, and also potential for point charges as well. So before we go to that part, okay, the third part is for capacitor later on. So before we go to the point charges, I think we haven't done with the examples yet. So let's see the examples again. Wait. Okay, here, this is where we stopped the other day. Okay, for this example 4, I think again we have discussed about this question. If you have done, congratulations. And then if you haven't, okay, so try to look at the question again. And for this question, for example, when you see this term, uniform electric field. So please understand that when you have this word uniform electric field, it will only refers to the parallel plates, because only in between of the parallel plates you will have a uniform electric field inside. Okay, and then for the parallel plate, like I said to you the other day, parallel plate can have the assemble of the plates like this, where you will have your electric field to the right. You may also have it in terms of something like this, where the plates is connected this way. It should be, maybe this is positive and then this is negative. So when you see this way of assembling the plates, means that the electric field is always coming out from positive and then go into the negative, and this will have the electric field going down. So what are the differences between this and this? First of all, you will have the equation becomes a little bit different. So in this case, your electric field is going downwards, and the equation becomes delta V over delta Y. So even though, okay, in general, you may write it in terms of V equals to ED. D means the distance. Analytically, you need to think first whether the electric field is horizontal or vertical. So this is another way, okay, for you to think critically, okay, before you make the calculation. Okay, and then like I said to you previously, since the previous semester, sometimes the question might not give you figure, so it's always your job, okay, try to sketch according to what the question gives you and work from there. Okay, so in this case, for this example 4, it refers to this one where the electric field is going to the right, and then you will only have potential difference only if the charge is moving horizontally, either to the right or to the left. So if the charge is moving vertically at that particular point, okay, even though it is moving vertically, but the x distance from the plates is maintained. So when there is no change in x, means that there is no potential change in potential difference. So try to do example 4 again, and then for example 5, I think this one you can if you haven't done this before, okay, let's just do it quickly together, because this one is actually very simple. So how to do it? The question is giving you an ion. So this ion, you don't know yet what type of ion, because ion you can also have positive and negative as well. And then it accelerates through a potential difference which has a positive V, and then it is having a potential energy which is negative. So the question is asking you what type of charge you are dealing with. So since you are given with delta V, and then you also have delta U. The only equation that combines these two together or relates energy and potential is given by U equals to QV. So by using this formula, rearrange to get the Q as your head of equation, and then after you calculate, you will see that you are left with negative sign in the answer. So that negative sign will refer to what type of charge you are dealing with. So right now the charge should be negative, and then the magnitude is given by the number. And then again, when you see this formula U equals to QV, this is different than what than the formulas that you have in chapter 1. In chapter 1 you have the Q with modulus, okay, but in chapter 2 you normally don't have any modulus. So to show that, okay, the energy and the potential, you need to consider the plus and minus sign in the calculation. It will be important because plus and minus sign will react differently in the electric field. So that's why, okay, we need to consider the plus and minus sign as well. So this is the example 5. So if you haven't done, okay, you may try it later. So right now we are going to go to electric potential. Okay, so for this electric potential of point charges, and also just a little bit on equipotential line and surfaces. So you will not calculate for equipotential line. Equipotential line is just the line that I want you to know, okay, where the potential is the same. Why I said it is the same? Because when you have this word equipotential, this equi means equal, okay, that equi means equal. And then the electric potential of for a point charge, again, it will only refer to two type of charge. You will deal with positive and negative. That's it. And then again, okay, please try to see the differences between the formulas that we have from chapter 1. Okay, first of all, we are going to determine the expression for the potential energy and potential for point charges, and then see the equipotential lines and also solving problems. So first of all, we are going to, I'm going to derive with U, okay, U and V for point charge. What we have done previously is only for parallel plates, now for point charge. So first of all, let's say you have a big charge and a small charge. A big charge Q is located at the origin, and a positive test charge, a positive Q naught, is held at rest at a certain distance RA from the origin. So again, when you have this term test charge in physics, test charge is something that we assume as a very tiny positive charge, okay, to help us to come up with the formula. Okay, so to derive the formula, there are some assumptions and there are some things that need to be assumed before we can derive for the formula. So in physics, normally we will start with this positive test charge. Okay, so the big charge is Q, located at the origin, and then you have a smaller charge at a certain distance from the big charge. And in this in this part, okay, you know that when the type of charges are positive, the small charge is positive, the big charge is also positive. So because we take that the positive charge is basically very tiny and very small, so due to the big charge, which is the positive charge here, the big charge will have electric field that is surrounding the charge as well. So this is what you have. Okay, this is the big charge, and the tiny charge here will react to the electric field in the surrounding of the charge. So because it is positive and positive, of course the smaller charge will be repelled. Okay, we take that. Okay, some of you might assume that, will the big charge not move at all? It may move a bit, but that is maybe very small movement. So maybe we ignore the movement of the big charge, but we assume that for the motion, it will be bigger motion for the positive test charge because it's tiny and it will react with the electric field of the positive charge. So positive and positive, it will repel, and then when it repel, somehow, let's say, it will move from point A to point B, like that. So when it goes from point A to point B, it means that as you know, when the charge is moving, it means there is a certain work done to move the charge. So what is the work done to move the charge? And then we are going to start from there, okay? And then it will move from point A to point B, for example. So how to come out with the work done? And some of you might think, why do we have to calculate for the work done? Again, the work done from point A to point B will also indicate the energy of the charge to move from point A to point B, because we know that from work done, the relation is W equals to negative delta U. Okay, so even though we have this formula in the parallel plates, like I said to you, it is also interrelated with point charge as well, because in the plates also the charge is moving. Okay, it's just that the formula might be a little bit special there. Okay, but for the point charges, okay, we also have this one, but to calculate for the U is a little bit different for the point charge. I will show you later. And then for the forces experienced by this charge, okay, on the positive test charge itself, due to the big charge, you will still have this Coulomb force. Okay, this is coming from our chapter 1. Force equals to K Q1 Q2 over R squared. So this is still our force, Coulomb force in between of the two charges. So what do we do with this one? Why do we need to relate with the force? Because I know there are some of you who will feel like, what? Do we have integration in physics now? We do, but you are not going to use it. You are not going to integrate it right from the beginning. No. Okay, I will show you what are the equations that you need to use in physics, but this one is just the derivation, so I need to show it to you this. So the work done by the electric field in moving the test charge from point A to point B is actually using the integral from your calculus. I mean, if you have studied mathematics, so you know this is the integration, right? So work done is basically equals to Fs. Okay, so when W equals to Fs, in terms of the charge motion just now, it should be F multiplied with the distance covered, dr. So in this case, we said that it is starting from Ra to Rb, and then what do we do here? This force is basically the Coulomb force that we have. F equals to K Q1 Q2 over R squared, correct? But you need to only integrate the distance. So the K Q1 Q2 will be bring outside. So from there, you will need to only integrate 1 over R squared dr from point A to point B. So this is what we are going to work on. Okay, the integration is done for the distance from point A to point B, and these are the mathematical steps. Okay, and then from the derivation here, okay, I hope you still remember your integration, okay, to get 1 over R and everything here. And supposedly these are not the things that you need to remember, of course. For the charge, okay, we will just consider U equals to K Q1 Q2 over R. So this one is coming from here. So this is basically U initial minus U final, okay, like that. So what do we have from here? U for point charge is taken as K Q1 Q2 over R. So if you don't really want to see the derivation, okay, I will just keep you to the real equation that you need to use for electric potential energy of point charge. So I want you to highlight this part. For point charge, it should be U equals to K Q1 Q2 over R. So in this case, if you compare with the Coulomb force just now, okay, Coulomb force have K Q1 Q2 over R square, but electric potential energy, you don't have modulus, you don't have the square distance. So this is what I really want you guys to highlight. Okay, energy will have K is still the same, your Coulomb force constant, and then you will have Q1, Q2 over R. Here in this case, your Q1 and Q2 comes without modulus. So you need to actually consider all the plus and minus sign of the charge. And R here without square. There are lots of students made a mistakes previously. So please write the formula carefully. That's why I really want you guys to differentiate well between U, V, E, and F. Okay, and then starting from U here, we still have the same connection from the parallel plates. U equals to QV for parallel plates. But from there, we need to derive. Okay, we derive things until we get this formula. V equals to KQ over R. So for point charges, okay, for point charges, the equations that you need to use for potential energy and potential is given by the one in the blue boxes here. U equals to KQ1 Q2 over R for potential energy, and then V equals to KQ over R for potential. Okay, so in this case, the other thing that I want you to highlight is that, okay, U and V is not a vector. So you don't need to justify the direction at all. Listen here carefully, highlight this part, write in your notes. U and V is not a vector. They are not vectors. Means that you don't really need to think whether they are repel or attract. Where is the direction? Do you need to use vector? Not in this chapter. Okay, so you just need to consider plus and minus for the charge, and that's it. Okay, and then for V, it comes with KQ over R. So that means for every charge, you will have its own potential. Why you have potential for each charge? Because again, every charge has electric field. So when they has electric field, means that that will become the source of energy. If you put any charge in the surrounding, then it will make the charge to accelerate to some other points. So here, okay, if the question asks you to find the net potential, for example, the net potential of a point due to a group of point charges can be calculated by summing all the potentials. So let's say you have three charges, Q1, Q2 and Q3 here. Okay, see this carefully. If you have Q1, Q2 and Q3 like this, means that how to calculate for the net potential. So I put here summation, okay, to show that it is a net potential, and then you just add them up here. Okay, add all charges will have KQ over R. So Q1 is KQ1 over R1, and then follow suit. Let's say, okay, I'm giving you one example. Let's say you have Q1 is actually positive, Q2 is negative, Q3 is negative. Then what will happen? Okay, you don't need to check with the direction. I told you this just now. So what is actually your steps to find electric potential? Okay, so what you need to do is for this part, it is better to write it this way. It becomes K, and then you have Q1 over R1. Okay, be careful, you don't have square, plus with K, and then make it in the bracket negative Q2. So I said this just now, you need to consider plus and minus in the calculation, then make it over R2, and then again for R3, for Q3, it is also negative, then make it like that, negative Q3 over R3. So when you make the calculation for potential, you need to consider plus and minus sign of the charges. Okay, so that's it. You don't need to justify the direction at all. You just need to find the summation of all potentials, but you need to consider plus and minus sign. Okay, so that's it. Okay, we're done with U and V for point charges anyway. Okay, so let's start with the example. So the question is, calculate the electric potential at point A and point B due to the charges Q1 and Q2 as shown in figure. So in this case, okay, I'm giving you 2 minutes for you to try to work this problem. Okay, I'll try to give you the guideline along the way and try to find the answer. Okay, what you need to do is find what is the V at point A, what is the V at point B. Why you need to find V? Because the question says calculate the electric potential. So if it is only electric potential, means that you are calculating for V. Okay. If it is electric potential energy, then only you calculate for energy lah. Okay, so right now it is electric potential. So what is your answer? Okay, I'm giving you 2 minutes. Try to work this one. Okay, I will give the guideline along the way. So you try to do it first. The answer. A. B. All right. So some of you might think that, so actually what we should do, okay, so let's look at point A. Point A is asking you to find what is the electric potential at point A due to charge 2 and charge 1. So charge 1 is negative, charge 2 is positive. So how to write your summation of V? So since you have two charge, means you just need to add what is potential from charge 1, what is potential of charge 2. That's it. So put it in the calculation. K, Q1 is negative, then put it there. Negative Q1 over the distance. What is the distance? It should be 60 from, between the point A and charge 1 is 60, but change it to meter. That's it. Okay, so proceed with that. You should be getting this number. Okay, I put the answer already there. So plus with, since Q2 is positive, then just make it as Q2, and the distance between Q2 and A is 0.3. So yeah, that's it. And then I put there VB equals to 0 joule. So why do you have it as 0? Then yeah, try to find your answer and then see why I put the answer for VB is 0. Okay, Q. Okay, I put a simplified version of the calculation actually. Okay, so if you feel like this way of writing the formula is quite alien to you, you can just do it the same as A. It's just that to show for VB, K is actually constant, so it should be the same. R should be the same because from B to charge 1 is 40 centimeter. From B to charge 2 is also 40 centimeter. Then you can just factorize it out. Then K over R is maintained outside, but in the bracket you have Q1 minus Q2. Why is it minus? It's because Q1 is, it should be Q1 is negative, Q2 is plus. So negative Q1 plus Q2, they are coming with the same value, 50. Okay, the magnitude is the same, but the charge is different. So Q2 minus Q1, this will bring everything to 0. So that's why you will have at VB, it is equals to 0 there. Okay, so I hope you have the answers the same. So this is 0 joule, and Okay, now I would like to introduce to you why the point B, at point B, you will have it as 0. Okay, there are conditions like this. If the distance is the same and it is coming from two opposite sign charges, one is positive, one is negative, means that there will be one possible points in the middle that the potential will be 0. So it's due to this calculation. So you already know why it comes, why the answer is 0, because one is positive, one is negative. So that's why it is cancelled off. So at point B here, as the distance is the same, the magnitude of the charge is the same but opposite, then you will have the voltage at that point, or the potential at that point, equals to 0. So it means that as long as, okay, the condition is like this, okay, say, listen here carefully. If the charge is the same but in opposite sign, and the distance are also the same, so be it here, here, or even here in the middle, as long as the distance is the same from both charges, okay, make it the same there, okay, and then to here, and here to here is also the same. At all points along this line, you will have potential equals to 0. Okay, and this is where you call it as equipotential line. Why? Because along the line, okay, from infinity to infinity, infinity y positive and negative, you will have v equals to 0 as long as the type of charge is opposite, the magnitude is the same, the distance is the same. So again, what is the line we call for y in the middle here? It is what you call as equipotential line. Okay, that's it. Okay, if you want to know the exact calculation for A and B, so here we are, we have it in the slide. So I hope you already got your answers. And okay, do not assume, okay, again, do not just assume the point in the middle should be 0. There are conditions, I told you just now, right? There are conditions like that. So it must be fulfilled like that in order for the potential right in the middle to be 0. But if the condition is different, you might have potential right in the middle. So I will do it in the with the calculations later. Okay, and then okay, that's it for point A and point B. And then I said that you cannot assume, right? So even though you assume maybe there should be 0 in the middle, I want you to show with the calculation. Okay, do not just write VB equals to 0. I want you to show with the calculation to show where they cancel out. Okay, then you will get all the marks. If you just write your final answer, you might not get the marks for the steps. So please keep it that way. Okay, and then all right, so there is another example 7. So example 7 is related to two sub questions. Okay, listen here carefully. The question is giving you two charges. One charge is Q, the other charge is negative 2Q. So that means the value of Q is the same, but for the charge 2, it's double the magnitude. Okay, so charge 1 is 4.11 and it is positive. Charge 2 is negative 2Q, then it should be 8.22 lah. Okay, here you need to have it as 10 to the power of negative 9. So this, somehow in the questions, they might write it as nanocoulomb. Okay, so nanocoulomb will give you this much of values of the charge. And then the question is, the two charges has 1 meter difference, okay, in between. And then you need to find the potential in the midway between the two charges. Okay, so you need to find the V. So again, if you want to find the V right in the middle, you cannot just assume it to be 0, because in this case, they are not the same. The condition is different. Even though maybe, okay, you are in the middle, it will be 0.5 from charge 1, 0.5 from charge 2. But right now, the magnitude of the charges is different. So it will not be 0 right in the middle. So you need to calculate for it. B, potential V vanish at some point between the charges, that is for value x between 0 and 1. Find this value x. So like I said to you, when you have one positive, one negative, there will be one point where the potential will be 0. But where is it? In this case, you need to find that location. In the previous case, the V is 0 right in the middle because there are conditions I already explained to you. So B, that will not happen here. So you need to calculate where is the location. So I'm giving you 3 minutes for you to do A and B. For A, actually you have to sketch the charges on your own, because the figure you have here is referring to question B. Okay, so 3 minutes for you. Okay, try to find the answer. Okay, let me write for you the answer as well. If you have any question along the way, please ask. Okay, please ask. Okay. V. Okay. Okay. Okay, that should be the answers. Any questions? Okay, so what you are going to calculate for the V in the midway, and the point where V vanishes should be equals to 0. So how do you calculate for this? So first of all, okay, if you see the calculation for U and V, it's basically quite simpler than what we did in chapter 1. Okay, in chapter 1 there are lots of things that you need to analyze, and then you need to discuss with magnitude and direction like that. But for U and V, somehow it's a little bit easier, okay, than E and F. Okay, so for A, how do you calculate for that? V equals to KQ over R. That should be the general equation. But to calculate for the potential in the middle, okay, in between of the two charges that we have in the question, first, okay, you have RA and RB, okay, and then it should be the same, which is 0.5. So this is what we have, because you want to find the location is right in the middle. So the difference is that, okay, you have KQ1 Q2 KQ over R. So from charge 1 it should be KQ1 because it's positive Q. From charge 2 it should be negative 2Q. Then you can factorize Q outside, then you can have as 1 and 2 in the bracket. So from here, proceed with the calculation, you will get negative 73.9. To calculate for B, since there is one point in between of the two charges that the V will be 0. Okay, so the thing is, okay, listen here carefully, you will always have V equals to 0 for the charges where the signs are opposite, and you can locate for that position. So if the question says something like V vanish at certain position in between of the charges, okay, means that you need to set the potential equals to 0. So in this case, you have KQ over X, and then you have K negative 2Q over 1 minus X. Why do you have this one? It's because previously in the figure, we already set P is here somewhere in between of Q and negative 2Q, and set that as X, because we don't know what is X. So means that you will need to find what is the distance from P to charge 1 and from P to charge 2. So it's something like that. And then if you already set X from Q1 to P, means the remaining should be 1 minus X for charge 2Q to the point P. So that's how we calculate. Okay. And okay, proceed with the calculation. Okay, proceed with the calculation. You make everything equals to 0, equalize this thing, and then rearrange with the mathematical steps. You should be getting X equals to 1 over 3 meters from Q1. And as you can see, okay, as you can see here, we normally put the point that will be 0 near to the smaller charge. Of course. Why? Because smaller charge has less electric field. Bigger charge will have more lines of the electric field. Means that the electric field, electric potential there will be bigger. So if you want to find points where the potential will be 0, most probably it will be nearer to the smaller charge. Okay, nearer to the smaller charge. Okay, so again, then you should be getting this answer 1 over 3 meter, and you should know that it should be from Q1. Then the remaining distance should be from Q2. So yeah, that's all you calculate. You can calculate for A and B. Okay, any questions before we go to the next example? Are you guys okay? Still breathing there? Or sleeping already?
I'm still here.
Okay.
But I think I'm going to have to revise this on my own later. Seems not to be sticking with me at the moment.
Okay. So there are some of you who are still with me. Thank you. Okay, those who have questions, okay, do not feel shy to ask questions, all right? Okay. For the next example, okay, it's related to minimum work done by external force to bring a charge from infinity to 0.5 meter from charge Q. So that means you have one charge. Where is my cursor? Mana cursor? Okay, itu. Okay, so what you will have is you have charge Q2. Okay, it's positive, and you see that Q2 is 20. Q1 is 3. So basically 20 is big. You want to bring Q1 near to Q2. So Q1 should be very far, and it's still positive. Okay, I make it a very small Q1. So this is Q1. And then you want to bring this from infinity, means it's a very far away distance towards a point which is 0.5 from charge 2. So this is the initial position. This is the final position. So how do you calculate? And you want to calculate for the work done. So first of all, in terms of previous semester, we normally calculate work equals to Fs. But in this semester, listen here carefully. In this semester, you are dealing with point charges. So when you deal with charges, your work done is always equals to negative of the internal energy or electric potential energy. So in order for you to calculate for the work done, you need to find the delta U. So how do you calculate for this? The small charge is 3 microcoulomb, and then the second charge is 20 microcoulomb. So how do you do from here? Then the work done is equals to negative delta U. So how do you bring to this calculation? So delta U means final minus initial. Okay, final minus initial, but final position is here 0.5 near to the UA, and then initial position is from the infinity. So you bring it from, you just plug in the number. You will have negative K Q1 Q2 over R infinity, and then minus with Q1 Q2 over the distance from the second charge. So this is the distance. The distance from the second charge starts with from infinity and then go to 0.5 from the charge 2. So you see here Q1 Q2 over R infinity. Infinity means the distance is very big. So when the distance is very big, what will happen to the calculation? Okay, you can safely say it is almost zero. Okay, so you can cancel this part. So when you cancel this part, then you have the equation becomes K Q1 Q2 over R. So this is your equation to find the work done and also coming from electric potential energy. So Q1 is given, Q2 is given, the distance right now from A is just 0.5. So you will get your answer as 1.08 joule. So that should be the answer. Okay. Any question? Okay. Let me check the chat.
Nothing particularly interesting going on in the chat.
Okay, it's okay. All right. Judah? Okay, slowly dying. Okay. Arif is sleeping. Sweet dream then. Okay. And then, okay, that should be, for example, and then we're done with the point charges. Okay. The next part is actually equipotential lines. For equipotential lines and surfaces, actually I have explained to you a little bit about the lines that has the same potential. So starting from the parallel plates, okay, starting from the parallel plates. So for positive metal plates and negative metal plates, here in the middle you will have electric field. So this electric field, you can see that the line for the electric field is coming from positive to negative, means it is horizontal. So like I said to you previously, okay, positive metal plates is what you call as high voltage. Negative metal plates is what you can regard as low potential, okay, low voltage. So coming from left to right, you will see here the voltage is slowly decreasing and becomes zero. So in order for you to have potential difference, okay, potential difference is delta V. You can only have potential difference when the charge is moving either to the left or to the right or to the left. So if the charge is moving from certain position A towards position B here, at this point the line has 15 volt. So even if it is moving along the line upward or downward, it is still on the same line where the voltage is 15. So you won't have any potential difference. So in that case, okay, the potential difference here is 0. Okay. And okay, so all the green lines here will show you that this point is having the same potential at all points. Okay, so the same goes to the point charges. Okay, the point charges is having the equation V equals to KQ over R, right? So you say that this is KQ over R. Okay, R should be the distance from the charge. So since for point charge, the distance can be any point around the charge. So in that case, you will have the equipotential line is around like this. Okay, so all these lines will show you the potential is the same, unless okay the charge is moving from a certain distance for from this point to this point, or from A to B, like that. So in this case, then you will have delta V. Okay, but if it is moving from here to here, for example, okay, at this point your delta V will be equals to 0, and that line is what you call as potential energy as well. If you put two charges together, so these are the patterns, and the lines also show you the V is equals to it's the same on the line. Right in the middle here, okay, right in the middle here, maybe, okay, V is equals to 0. Why I said maybe? It should be due to what is the magnitude of the charge and what is the magnitude of this charge. If the magnitude is the same but the sign is opposite, then right in the middle voltage is equals to 0. But if they comes with different magnitude, then you will still have some value of the potential, and all the potential will be the same on all lines. So that should be the equipotential line and surfaces. You don't really need to calculate for this one. It's just want to let you guys know where is the potential lines that are having voltage the same in all points. Okay. All right. So this is the what do you call it? The statements coming from the illustration, the figure just now. Okay, so I'm going to introduce to you about capacitor. Okay, for this one, for capacitor, it's about, okay, when we talk about capacitor, okay, capacitor is actually it's already application. What we do in parallel plates is basically theory. Okay, but parallel plates is theory where you need to justify the direction of electric field and everything. But when the question already starts giving you capacitor, it's basically already the application. Why is it application? Because in capacitor, we don't really care about where the where the direction of electric field anymore, because capacitor is an element that you connect in the circuit, and normally it is connected in AC circuit. What is AC circuit? It should be alternating circuit. Okay, alternating circuit is where you will connect the circuit with something like generator. Generator means it can provide the power supply to the circuit in both direction. It can be maybe clockwise direction, also counterclockwise direction, or in terms of the loop. Okay, we were going to learn that later. And so for the capacitor, okay, it's already the application of parallel plates. And then we are going to look at dielectric. What is this? What is dielectric? I think you have heard about dielectric before, right? Have you learned about capacitor and dielectric before? Anybody?
Capacitor sounds familiar, but not dielectric.
I see. All right. Thank you for that. Okay, so in order for us to study about capacitor, okay, we know that capacitor is a small element that store energy. Okay, but in order for you to enhance the capacitor, we can insert dielectric. So I will explain to you about dielectric later. And I said this just now. The capacitor has a function of storage electrical energy. So this is the function of capacitor actually. Why we need capacitor? Because capacitor can store energy. What type of energy that's stored in the capacitor? Okay, so it depends on the capacitor that we have learned in the parallel plates. So if you can think again, between positive and negative, okay, between positive and negative metal plates, we have in the middle, what do we have in the middle again? Anybody? Tell me. What is it? I'm trying to right here for you. What do we have in between of positive plates and negative plates?
We have potential difference.
Potential difference. Other than that,
We have electric
Electric
field.
field.
okay, congratulations. Okay, electric field. So this electric field is coming from, okay, here it is. Potential difference it's due to the charge movement. Electric field is what you always have when you build up all the positive charge on the metal plates and all the negative charge on the in the other metal plates. So whenever you have all the positive charge here, all the negative charge here, you will automatically have electric field. So this electric field is what you want to have in between of the metal plates. So in other words, the storage of electrical energy in capacitor, it comes with electric field. So in other words, the energy that is stored in the capacitor is in terms of electric field. So you want to store the electric field in the capacitor. So in this case, okay, we want to know what is the factor that will affect the capacitor and how to enhance the capacitor. What do you mean by enhance the capacitor? You want to make the energy stored in the capacitor more than what it can. Okay, so so we will come to that, of course, as well. Again, why do we need the capacitor? Because there will be energy stored in the capacitor, and we normally have capacitor in all electrical appliances. Why do we need this capacitor? Because the energy is stored in the capacitor. Why do we need the energy? For example, you have something like fan. Okay, something like fan. If you don't have any capacitor, you just switch on the circuit. It will take some time for the fan to move, for the fan to rotate. Because in order for the fan to rotate, the circuit might need to wait for a while. Okay, for the current to be stable, then it will rotate the fan. If you have capacitor inside the circuit, capacitor already has energy stored in it. So that means it will help with the circuit to stabilize or to make the current stable in a short time. So that's why, okay, when you switch on the fan can easily rotate like that because the capacitor already has the energy. Okay, and it will rotate straight away. So if the fan taking a lot of time to rotate, you might need to change the capacitor. Okay, there might be something wrong with the circuit. If not capacitor, it might be due to something else, of course, because there are so many components in the circuit, but it might be due to the capacitor. Okay, so that's the function. Okay, we need to have the capacitor in the circuit. And then what do we have here to provide the expression for capacitance of a capacitor? So battery will have the unit in terms of voltage. Capacitor will have the unit in terms of capacitance. There will be some unit later, but the value of the capacitor is capacitance. And then explain dielectric, and also to calculate for the energy stored in the capacitor in terms of electric field, and then solve problems related to this one. So what do you learn? What you have learned for parallel plates, somehow it can be used in capacitor, but for capacitor you will have a designated formulas only for capacitor. So that's why I said that semester 2 is quite interesting and different than semester 1, because semester 2, if it's related to that particular area, you only have that equations to be used. Okay, you don't have questions right from the first chapter related to second, related to third, and so forth. Okay, so let's see how to calculate for the capacitance. So first of all, capacitor consists of pair of metal plates of area A. So this is another important thing, separated by small distance in between of the metal plates. And okay, this is what you call as the parallel plate. So in other words, for capacitor to be used in the circuit, okay, capacitor must have certain area Why do you need the area? Because this area will make all the plus and minus sign being built up. Okay, positive or negative. So negative should be on the other side lah. Okay, that should be it. And then there should be separated by small distance in between. So there will be, the area and the distance will be the factors affecting the value of capacitor. So I'll show you with the equations later. So just know that capacitor consists of metal plates, of area given, and also a distance in between of the two metal plates. And I would like to say about this thing, area. Capacitor comes with a lot of or various types of shape. It can be circle, it can be square, it can be rectangle, it can be any type of shape. So in other words here, the area here, it depends on the question. So if your question is giving you dimensions, means you may calculate it as rectangle or cube. Okay, or square, sorry, or square. But if they give you in terms of radius, they might comes with circular shape. So just know that the area depends on the question as well. Okay, and then for the circuit symbol, so the capacitor has two straight line. Okay, two straight lines, and it should be equal in height. Okay, don't make it shorter, one short, one long, because one short, one long will show you battery. Okay, so circuit symbol here will show you this is capacitor. So this is the symbol. Okay, and then what can you calculate for the capacitor? Okay, before we go to the capacitance, I want to introduce to you the first equation for capacitor. For parallel plate capacitor, so the question will give you this term. So once you see this term capacitor, you are free to use this formula. When PD, which is potential difference, or you call it as voltage, is applied to a capacitor, it is charged. So to charge a capacitor, okay, this is how the capacitor is charged. So starting from this battery, you see that this is positive terminal, this is negative terminal, and then the negative will be built up here. Okay, so the negative or electron all will be accumulated at one plate, and the other charge will be, positive charge will be built up in the other plates. So one plate is positive, one plate is negative. So charge Q acquired by each plate is directly proportional to V. It means that initially, what do you call it? Okay, listen here carefully. Initially, the capacitor has no energy at all. No electric field at all in between of the parallel plates. So if there is no electric field at all, means that the capacitor is what you call as fully discharged. Okay, fully discharged means your battery is out. Your handphone is out of battery at all, so you cannot use anymore. So if you connect that to a battery, so the battery will charge the capacitor. So when the battery charge the capacitor, it will take some time. Of course, we will come to the charging time later, but once you charge the capacitor, if you connect that to a battery or to a power supply, to a voltage, the battery, okay, will gain voltage as high as how much the battery is supplied. So if the capacitor here is fully charged when it is connected to this battery, then you will say that the voltage here is the same as the voltage difference from positive plates to negative plates. Okay, so how to calculate for the charges on the plates? This is the equation. Q equals to CV, okay, which is the number of charge built up on the plates, and then C is the capacitance of the plates. Capacitance of the capacitor, I will show you later how to calculate for it, or you can just write it in terms of C equals to Q over V. So the amount of charge depends also on how much is the power supply to the circuit. The unit for the capacitance is farad. Okay, it is farad. So please use this as the unit of C, and normally, okay, normally it comes with either microfarad or nanofarad. Okay, this is normal. Okay, this is normal unit you may find for the capacitor, and also a picofarad. You can also find pico. So please be familiar with these prefixes: micro, nano, and pico. I think to the power of 6, to the power of 9, and to the power of 12. Okay, so be careful with the calculation later. The unit is farad. This is SI unit. Okay, this is SI unit for capacitor. This equation is for you to find the capacitance when you are given with voltage and the number of charge buildup. On how to calculate for the capacitance of the capacitor itself, because it is depending on the area and also depending on the distance between the two charges, the two plates. Then the equation is this. It is given by C equals to E naught A over D. Okay, so what is this C? It is the capacitance in farad. E naught is what you call as permittivity of free space. So this should be a constant. Okay, E naught is a constant. And then why do we have the constant? Again, when you have this thing, permittivity of free space, okay, E naught is somehow the constant you have when you deal with charges. Okay, and in between of positive metal plates and negative metal plates, you do have the electric field in between, but you don't know what else we have in the space. So they said, okay, we need to consider consider that in the calculation as well, because they might affect the value of the capacitor. So we put the constant in the calculation. So we have C equals to E naught A over D. A depends on the type of capacitor. If it is parallel, if it is circle, square, rectangle, or any other shapes. And then D should be the separation between the two plates. So in order for you to enhance, okay, so like I said to you, you can do something to make the capacitor great, okay, a great capacitor. So you can increase the value of electric field inside the capacitor. So to increase the capacitance, you may do something, maybe make the area bigger or make the separation smaller, like that, because the capacitance is directly proportional to the area, inversely proportional to the distance. Okay, before I forgot, this one, E naught, it should be 8.85 times 10 to the power of negative 12. I don't know which calculator you use, but you can get this value in your calculator as constant 32. Okay, so please check this in your calculator. This constant can help you to make your calculation easier. Okay, constant 32 is E naught. So E naught is your permittivity of free space. That should be a constant when you deal with the parallel plates here. Okay, capacitor. Okay, other than that, I said that for the capacitor, you can have, you can change either area, make it bigger and smaller separation, because you know that when you make the separation smaller, okay, capacitance will be higher. So right now, can you have positive plates and negative plates really near to each other, very close to each other and attached to each other? Can we have that? Because the smaller the space, the higher the capacitance. So can you put the metal plates in touch with each other? Anybody knows?
I don't
Why?
think so, because then you would have little to no potential difference.
I see. Correct. Thank you so much. Okay, so partially, it is correct actually. Another thing is, I think the more suitable answer should be, we cannot make positive plates and negative plates attached to each other, because you need to have electric field in between. So if they attach to each other, you don't have electric field. If you don't have electric field, then you don't have potential difference. Okay, so that should be the analytical thinking behind that. So even though you can, I mean, in order to enhance the capacitance of the capacitor, you can make your distance smaller, but it cannot be attached to each other, because when they attach to each other, there will be no room for the charge to move. Okay, so because when the charge don't move, you don't have electric current. Okay, so that should be the idea of having a little space in between of the metal charges. And then the area as well. As you know, the area is one of the factors to increase the capacitance. But if you make the area bigger, so if your capacitor is bigger, means that your circuits will be bigger. So in order to increase the capacitance, you need to also know where to use this capacitor. So you don't want to have a very big handphone to carry everywhere in order to have the capacitor inside. So that's why things that we have right now, it's getting smaller and smaller, but there are things that can enhance the function of each element we have in the circuits. Okay, so I hope you can relate to that. Okay, because you are the inventors of the future, so need to think critically of all the things that we have. Okay, and the last thing in capacitor I want to introduce to you is the voltage or the potential in between of the two metal plates. Starting from E equals to V over delta X. Previously, we have the negative sign as well in the calculation. We note that positive metal plates is high potential, negative metal plates is low potential. So in this case, okay, we put that, okay, here maybe V is full, and then at negative plates V is 0 because it's low. But in terms of distance, okay, maybe we start with the charge move from this point to that point, okay, the distance. So it's starting from 0 to certain position on the right. So by using these parameters and also the values, we put that back into the calculation. We have 0 minus V, it should be from low voltage finally, and initially it should be full voltage, and then divide by D. Then you have this minus sign and this minus signs being cancelled off. Then you will have V equals to ED. So this one will be used in capacitor, although you have it in parallel plates. In parallel plates, because it's theoretical, we do need to have the plus and minus sign. But in capacitor, it's already the function, so we don't need the minus sign anymore. Okay, because for capacitor, for whatever position it is connected, okay, we don't really want to know which direction of the electric field direction is going into anymore. Okay, so 3 equation for capacitor. First of all, you have this equation, Q equals to CV, and then you have another equation, C equals to E naught A over D, and then the next question is V equals to ED. So this is the 3 equations that you will use in capacitor, and yeah, we will use these 3 equations whenever you see this word capacitor. Okay, so the question will tell you in specific whether you only deal with parallel plates or you deal with capacitor. Okay, so one question for you to do. Okay, let's do it together. I think I might use this as our final example for today. So we will continue with the electric in our next class. Okay, so example 9. So let's do this together. Okay, come on. Our final example and exercise for today. I hope it's okay with you if we stop here for today, and we'll continue with the electric later. Okay, so the question is, calculate the capacitance of a parallel plate capacitor. So the question will give you a direct question related to capacitor whose plates are 20 centimeter by 30 centimeter. So this should be the dimension. This will be used to calculate for the area, and separated by the distance of 1 millimeter air gap. Why do you have this air gap? Means that you don't have anything else in between of the metal plates. So use this to calculate for the capacitance C, and then the charge on each plate is what you are going to calculate next for Q, and then calculate for electric field. So I put here the value of E naught. Maybe you didn't write it just now. It should be 8.85 times 10 to the power of negative 12. So use that in the calculation. Negative 12. Or you can get from your calculator constant 32, and then try to find the answer. I give you the answer here. 53 picofarad. So please know what is pico. If you are not comfortable giving your answer in pico, keep it in the long form is fine. Okay, 6.4 times 10 to the power of 10, negative 10. C. Charge. Okay, done. What is the electric field between the plates? Okay, this is the answer. Okay, there is another thing I want to explain to you. 10 to the power of 4. So calculate first. Actually, for A, B, and C, you will make use of the three equations that we have today. I mean for capacitor. So use all the equations for capacitor to find C, Q, and E. V over M. Okay, done. That should be the answer.
Miss.
Yes, question.
So not really. So quiz tomorrow will be covering until what you taught today, or the entirety of chapter 2?
No, only until capacitor.
Until capacitor. Alright.
Only capacitor.
How many questions are there?
4.
4. Alright.
Alright.
Thanks, Miss.
You're welcome. Okay. First of all, you calculate for the capacitance. It should be C equals to E naught A over D. And then Q equals to CV for you to calculate for Q. And then you will calculate for electric field by using V equals to ED. Okay, so I hope you guys already found your answer. Raise your hand if you already finished. Although I cannot see. Are you doing this together with me? Oh, okay. Some of you already give me some reply. Thank you, Farid, Afzal. What is the unit? What is unit? Unit. What is the unit? Amir. What unit? Unit apa ya? Farad. Farad for capacitor, coulomb for charge, and V over M should be volt per meter for electric field, or you can also use N over C, no problem, because electric field is also Newton per coulomb. So let's say you cannot remember V over M, but you use N over C instead. Both are correct. Okay. Okay, so got it. Okay, Afiq already got the answers, so I'll just show you all these answers. This is where we have capacitance, Q and E calculated this way. And then, okay, because you already finished calculating. Okay, listen here carefully, listen here carefully, listen here very, very carefully as well. You see the question here. What is the charge on each plate if the capacitor is connected to 12-volt battery? Some of you might think that charge on each plate, because you have two plates. You have one positive plate, one negative plate. Do you have 2 times 2? The answer is no need. Why you don't need to calculate for, you don't need to multiply with 2. Okay, here it is. The amount of charge built up on positive plates is the same as the amount of charge built up on the negative plates. So let's say this is the amount of charge positive built up on the positive plates. It should be the same amount of the negative charge built up on the negative plates as well. So you don't need to multiply by 2, because they are actually in the same amount, because they should come in pair. one positive and one negative. Okay, initially they should be neutral. So by connecting the capacitor in with the battery, you are actually separating the charge. All positive charge will go that way, all negative charge will go the other way. So you don't need to multiply by 2. What you calculate is already the amount of charge built up at each plate as well. Okay, so that should be, some explanation on that, because there are some of you will question this later on. Okay, and then to enhance the capacitor, what you will do is, next we are going to consider putting put something in between of the metal plates. That is what we call as dielectric. Okay, so dielectric is something that you put in the middle of the two metal plates in order to enhance the capacitor. So we will do dielectric in next week, and then that's it for chapter 2. Then we will also continue with chapter 3. I think chapter 3 is quite interesting, okay, because it's just a direct current chapter. Chapter 4 will come with a lot of calculations. So if you have time, try to read further for chapter 3 and chapter 4. And then for quiz tomorrow, it will only cover until capacitor. Okay, so that's all from me today. Is it okay if we finish the class right now? Are you okay with it?
Yes.
I think
Okay.
it's okay.
Oh, siapa tu? Baru bangun tidur ke? Okay, wait. Okay, so that's all from me today. Okay, again, tomorrow your quiz will be from 11 to 12. So yeah, prepare yourself. It will be through Yulen, and then just submit there as well. So as usual, okay, handwritten, and then please submit it in PDF. Okay, so let me check the chat box for a while. Okay, thank you so much. Okay, so thank you. Let me stop recording. Where is it? Oh, dah bertukar. Kenapa kat atas ni? Okay, wait. Okay, stop recording. Okay, done. Okay, thank you so much. Please do the satisfaction poll for your attendance today, and then I'll see you tomorrow for the quiz. Bye bye. Welcome. Okay, I'm sorry. I'm sorry if your brain is too tired, but I hope you get to learn something today. Bye bye.
Miss,
Yes.
Judah here.
Yes, Judah.
Um, as me said, right, dielectrics are separated by air gaps, right?
No. The parallel plate is separated by air gap.
But why not use like a vacuum?
Okay, Judah, if you have, in vacuum, if it is in vacuum, the charge cannot move. So it should be with certain air gap. So in air gap, you still have some values for the charge to move. If it is vacuum, then the charge cannot move there. Okay.
All right.
Okay. So later, okay, we are going to have more than air gap, because we can have a lot of things that you can put in the middle of the capacitor to help with the electric field. Then you will also can calculate for more capacitance. So when you have more capacitance, means you can store more energy for the capacitor.
But Miss, how do those vacuum variable capacitors work?
Again?
Those vacuum capacitors.
Vacuum capacitors. Let me read something on it first, and then I'll get back to you in the next class.
All right, Miss.
Okay, let me write something there. Vacuum capacitor. Okay. Thank you, Judah.
All right, Miss.
Okay, bye-bye.
Bye-bye.
Any other question?
I don't.
See you, Miss.
Wafi. Welcome. See, Wafi, you are not helping. Okay. Okay. Take care. Bye-bye. See you tomorrow. Good luck for the quiz.